Next question, what's the potential energy of a simple harmonic oscillator subject to a net force F equals negative kx? And actually I could put the net subscript on that. So what's the potential energy of this oscillator at position x? This is something that we covered a long time ago, that we've known for a while. Elastic potential energy, it's not just a formula, it's something you can derive. You should think about how that's derived. The result is potential energy is 1/2 kx squared, and we get that by integrating negative kx, the net force, with respect to x. This is a conservative force, so don't have room to write this. I'll come back and do this in a bit of a class extension. And I'm going to pause and write that down real quick. Have to remind myself, otherwise I might not get back to it. I'll say what it is. This is net force, this is conservative. So if we integrate the net force from 0 to position x, we're going to get negative 1/2 kx squared. That's the work done by a conservative force and moving from position 0 to position x, so that the potential energy change is equal and opposite to that. If the potential energy is 0 at equilibrium, then we get potential energy is 1/2 kx squared. Okay, now what's the potential energy at maximum displacement? Well, that's 1/2 Ka squared. Well, the maximum displacement is called the amplitude, which is A. And actually that's the magnitude of the maximum displacement. That's A. Maximum displacement could be A or negative A. Excuse me, kinetic energy. What's the kinetic energy then of a pendulum at equilibrium? Again, you should pause and answer this for yourself before you go on. Well, what you should have thought of is that the first of all assumption is an ideal pendulum, no frictional or other forces, no forces other than this, because this is the net force, so that the work done by non-conservative forces is 0. If that's a net force, since that's a conservative force, there are no non-conservative forces acting. And it then implies that the change in kinetic energy between any two positions is equal to the negative of the change of the potential energy. Well, if we release a pendulum from its maximum amplitude, it swings back for its maximum displacement from the position where its displacement equals its amplitude, and it swings back to the origin. The kinetic energy when you started here was 0, and the potential energy when you get to equilibrium is 0. So the change in kinetic energy between maximum displacement and equilibrium is equal to the negative of the change of potential energy over the same interval. Since we're going from maximum amplitude to x equals 0, change in potential energy is 0, the potential energy at the equilibrium position, minus 1/2 Ka squared, the potential energy at the extreme position. And then it follows that the kinetic energy change from here to here has to be 1/2 Ka squared. Kinetic energy was 0 here, so the kinetic energy here is 1/2 Ka squared. So again, kinetic energy at maximum displacement is 0. This is your change in kinetic energy. Implies that the kinetic energy at equilibrium is 1/2 Ka squared. Now, question, what is the kinetic energy at the point halfway to equilibrium? There's another one you should pause and work out for yourself. Think through it. Don't sit back as a spectator and watch it, because you won't learn as much. Although if you do, that's your privilege, okay? Some people can. Okay, well, halfway to equilibrium, x is 1/2 A, so the potential energy is 1/2 K times quantity 1/2 A squared, 1/8 Ka squared. I commented in class that you could have figured that out by simple proportionality. The potential energy is proportional to x squared. So if x becomes half of what it was, x squared is going to become 1/4 of what it was, so that the potential energy would be 1/4 of the maximum, or 1/4 of this, which is 1/8 Ka squared. Okay? Now the change in potential energy is equal and opposite to the change in kinetic energy. That's then going to be the 1/2 Ka squared minus the original kinetic energy, the new potential energy minus the old. and that's going to give us negative 3/8 Ka squared. And it follows then that the kinetic energy is 3/2 Ka squared. So now, what's the velocity of the oscillator at this point where the kinetic energy is 1/3 or 3/8 Ka squared? You should work that out, and you'll have plenty of time because I'm going to stop this clip, put the new board up. That's the question we begin the next clip with. What's the velocity at the point where, at the point halfway to equilibrium?